Why is this car so much faster than this one? Sure, it has a better engine, but how does it work and why is it better? Also, if you know a bit about F1, you know the key to their speed is also their shape, which makes them stick to the ground in corners. But again, how does it work exactly? Why this specific shape makes it possible for the car to stay glued to the track at such high speeds in corners? How can these cars reach over 350 kilometers an hour on the straights and take turns at 250? That's exactly where we are going to find out in this video. We are going to break down the math and physics that makes a Formula One car the fastest racing machine on the planet. To see what we need to cover, let's simplify our car down to a single point mass moving along our track. There are three fundamental physical barriers trying to slow it down. First is inertia. A Formula One car has mass, and Newton's laws dictate that it requires energy to change its state of motion. Second is aerodynamic drag. As the car pushes through the air, the atmosphere pushes back, and this resistance squares with speed, so we need energy again to keep the car in motion. Finally, there is the limit of traction. If the physical forces, like the centripetal force in turns, demand more grip than the tires can offer, the car slides. So to go fast, engineers must maximize engine power, manipulate airflow to reduce drag and to increase grip, and completely master the traction of the tires. To overcome inertia and drag, you need power. Lots of it. Let's zoom into the power unit of F1 cars, the 1.6-liter V6 hybrid engine. That 1.6 liters refers to the total volume swept by all 6 cylinders combined, and the V6 simply means those cylinders are arranged in a V-shape. We'll expand on the hybrid system later, but the real mystery is, how does this tiny engine produce over 1,000 horsepower when a similarly sized engine in your daily driver only hits 120? To understand the power, we have to look at the combustion cycle and graph the gas pressure against the changing volume inside the cylinder. This curve maps out the 4 strokes. First is intake, where the piston moves down to draw in air and fuel. Next is compression, where the crankshaft forces the piston up, shrinking the volume and squeezing that mixture. Then comes the power stroke. The mixture of air and fuel is ignited, and the explosion drives the piston down with massive force. Finally, the exhaust stroke, where the piston rises to push out the burnt gases. To give you more context, this is roughly what it looks like. This constant up and down motion is converted by the crankshaft into the rotation that drives the wheels. Now, mapping what happens inside that cylinder back onto our pressure and volume graph, let's figure out the actual mechanical work produced. In physics, work is fundamentally defined as the integral of force over distance. Inside our engine, the force pushing the piston down is equal to the expanding gas pressure multiplied by the circular area of the piston. If we substitute that into our equation, we get pressure times area times the tiny distance the piston moves, dx. But area multiplied by distance is simply a change in volume, dV. So, our work equation elegantly simplifies to the integral of pressure with respect to volume. This proves that the area enclosed inside this PV loop is the exact amount of mechanical joules driving the car forward. To generate massive power, Formula One engineers use turbochargers to cram dense air into the cylinder, violently spiking the peak pressure and expanding this area. Since power is work over time, spinning the engine at a blistering 15,000 revolutions per minute means they calculate this physical integral over 100 times a second across all 6 cylinders. This extracts extreme energy from the fuel, bringing us to thermal efficiency. While a typical road car hits 30%, a Formula One engine achieves over 50%. To understand how they hit that 50% mark, we can visualize the energy flow using a Sankey diagram. Imagine this thick band represents all the chemical energy contained in a drop of fuel. In a normal engine, over half of this band would branch off and vanish as wasted heat and exhaust. But an F1 car utilizes 2 brilliant pieces of engineering to capture it. First, the motor generator unit heat, or MGUH, sits on the turbocharger shaft, harvesting the massive rotational kinetic energy driven by the rapidly expanding exhaust gases to power a generator. Second, under braking, the motor generator unit kinetic, or MGUK, engages. When the driver brakes, an electronic inverter simply activates the electromagnets in the MGUK, creating a massive electromagnetic drag on the crankshaft that simultaneously generates electricity and forcefully slows the rear wheels. Both units convert this scavenged energy into electricity, storing it in a central battery. Mathematically, the amount of energy that can be recovered comes down to rotational kinetic energy. The energy recovered by the MGU-K is proportional to 1/2 times the moment of inertia times the angular velocity squared. Through regenerative braking, some of this immense rotational energy is transformed into electrical current. But harvesting energy is only half the battle. Deploying it is where the lap time is found. An internal combustion engine naturally has a torque curve that ramps up with engine speed, leaving a power deficit at lower RPMs. The electrical motors, however, can deploy maximum torque instantly from 0 RPM. By electronically filling in the gaps of the combustion engine's power delivery, the hybrid system creates an incredibly flat, perfectly optimized torque curve, giving the driver instant acceleration out of every single corner. But here is the ultimate paradox of building a 1,000-horsepower engine. Power is completely useless if you cannot transfer it to the ground. Let's look at a graph of available acceleration force versus vehicle speed. With the electric motors deploying, the car has a massive surplus of power at low speeds. However, there is a hard, mathematical baseline. This horizontal line represents our static mechanical grip limit, the maximum friction available purely from the car's resting mass. At low speeds, any power delivered above this limit is entirely unusable. It simply spins the rear wheels, destroying the rubber. No matter how perfectly we optimize thermal efficiency, our baseline performance is abruptly cut off. To bend this line upward and go faster, we must dive deeper into the physics of grip. The sole physical connection between the car and the track is the tire's contact patch, an area barely larger than a piece of paper. This brings us to the ultimate physical limit of grip, governed by the classic model of Coulomb friction. The maximum grip, or frictional force a tire can generate, is exactly equal to the coefficient of friction, a measure of how sticky the rubber and asphalt are, multiplied by the normal force, which is the physical weight pressing the tire down into the track. No matter how much torque the engine produces, if the force at the contact patch exceeds this maximum friction vector, the tire simply spins. But a Formula One car isn't just driving in a straight line. It has to brake, accelerate, and corner, often all at once. To understand how these dynamic forces interact, engineers use a concept called the friction ellipse. Let's plot this out mathematically. On our vertical axis, we have longitudinal forces, accelerating and braking. On the horizontal axis, we plot lateral cornering forces. The fuzzy, glowing boundary of this shape represents the transition zone of peak grip. But notice that this limit is highly dynamic. When you slam on the brakes, inertia forces the car's mass forward. This dynamic load transfer causes the front tire's grip capacity to swell, while the rear's shrink, completely altering your available traction budget across the chassis. The true mathematical challenge of driving arises when you try to do two things at once. What happens if you are braking at the absolute limit, sitting right on the edge of the ellipse, and then you try to turn the steering wheel? Adding the lateral cornering force vector to our longitudinal braking vector pushes the resultant total force vector diagonally. Look at what happens. The tip of this new vector extends completely outside our friction envelope. Mathematically, the required force has breached peak available friction. As the vector crosses this fuzzy threshold, the tire transitions from static grip to kinetic friction, operating at an extreme slip angle where the rubber can no longer sustain the track's demands. The grip gives way, and the car slides out of control. So, how do we solve this? If we want to corner faster and brake harder simultaneously, we simply need a larger friction ellipse. Looking back at our friction equation, the most obvious way to increase grip is to increase the normal force by making the car heavier. If we increase the mass, the ellipse mathematically gets bigger. But there is a fatal flaw in this logic. According to Newton's second law of motion, the force required to accelerate or turn an object is equal to its mass times its acceleration. If you add mass to get more grip, you simultaneously increase the inertia of the car. The required force grows at the exact same rate as the available grip, canceling out any advantage. We need a way to press the car into the track, creating artificial weight without adding any mass. The ultimate cheat code in racing is aerodynamic downforce. If we look at these real Formula One cars, they look incredibly complex. But every single winglet and carbon fiber floorboard is designed around two fundamental equations of fluid dynamics. Before we understand the car, we must understand the math. This is a Venturi tube. We are interested in what happens right here in the bottleneck, where the tube gets thinner. Common sense tells us a bottleneck should cause a traffic jam. But in fluid dynamics, at any speed below Mach 0.3, air doesn't compress enough to matter. So engineers treat it exactly like water, an incompressible fluid. This works perfectly for us because F1 cars top out around 350 kilometers an hour, safely below that limit. Since we can ignore air compression, we know that whatever volume of air enters the pipe, the exact same amount must exit. This leads us to the continuity equation. Let's take 2 points inside the pipe. Point 1 is before the bottleneck, and point 2 is inside the bottleneck. We calculate the mass flow rate for each point by multiplying the pipe's cross-sectional area by the speed of the air and its density. Because the air isn't compressing, we can cancel out the density on both sides, since it remains constant everywhere. However, because the physical area at point 2 is smaller, the air is mathematically forced to accelerate to push that same volume through the gap. But accelerating requires energy. In physics, the total energy of any closed system is simply its kinetic energy from motion plus its stored potential energy. For a flowing fluid, its potential energy is its internal pressure. Because energy is always conserved, the fluid's total energy must remain strictly constant, which gives us Bernoulli's equation. When the air rushes into the narrow throat, its speed increases, causing its kinetic energy to spike. To pay for that massive gain in motion without creating new energy out of thin air, its potential energy must drastically drop to balance the equation. In other words, faster moving air mathematically induces lower pressure. So, how does this apply to our racing car? Let's strip away the tires and the engine and reduce the car to pure geometry. Aerodynamically, an F1 car is essentially just the top half of that Venturi pipe. The flat asphalt acts as the bottom boundary. As the car violently pushes through the atmosphere, air is choked into the tiny gap under the floor. Following our equations, the air accelerates and the pressure plummets. Because the air pressure above the car remains at normal atmospheric levels, this mathematical pressure difference creates a massive downward force, sucking the car into the track. This is why engineers design F1 cars to sit so close to the ground. The smaller the gap, the faster the air has to travel underneath, which drops the pressure even further and generates more downforce. But the floor is only part of the equation. We must also add the front and rear wings. These are simply airplane wings turned upside down. As high-speed air hits their curved surfaces, the airflow is violently deflected upwards. By Newton's third law, this pushes the car down. But look at the flow. The air traveling under the curved wing moves faster than the air above it. Just like our floor, this creates a Bernoulli pressure drop. That pressure difference between the air under the wing and the air above it also generates downforce. These wings are vital because they are adjustable. By changing their angle, engineers can increase or decrease the downforce generated by a wing, which allows them to perfectly balance the aerodynamic grip between the front and rear tires. Now that we know how downforce is generated, we can mathematically calculate it using the downforce equation. Let's break it down. The first part, 1/2 density times velocity squared, is the exact same dynamic pressure term we just saw in Bernoulli's equation. It proves that aerodynamic force grows exponentially with the square of the car's speed. The A stands for the reference area, which is the physical size of the floor and wings we just looked at. And CZ is the aerodynamic coefficient, a multiplier determined by how aggressively engineers have angled those wings. Multiply them all together and you get FZ, the total aerodynamic downforce. But how does this help us corner faster? Let's bring back our friction ellipse. Remember our fundamental friction equation? Maximum grip equals the tire's compound coefficient, mu, multiplied by the normal force pushing the car into the track. Originally, that normal force was just the physical weight of the car, mass times gravity. But now, our Venturi tunnel and wings are pushing down as well. So we expand the normal force to include our new downforce variable, Fz. Watch what happens. Because downforce is tied to velocity squared, as the car speeds up, Fz skyrockets. The physical weight of the car doesn't change at all, yet our circle of grip massively expands, giving the driver supernatural traction at high speeds. All that grip we just created comes at a steep, unyielding mathematical cost. Downforce is never free. Its inescapable shadow is aerodynamic drag. To understand this, let us look at the drag equation. It has exactly the same mathematical form as the downforce equation we derived earlier. 1/2 times the air density, multiplied by a coefficient, now the drag coefficient CD instead of CZ, the reference area of the car, and crucially, the velocity squared. Notice that squared term. It is identical to the one in downforce. Both aerodynamic downforce and drag scale with the square of speed. Let's plot this. As the car accelerates, downforce increases quadratically, providing more and more grip in the corners. But aerodynamic drag also increases quadratically with that same v² factor. Because drag acts directly backward against the car's motion, it is the force the engine must constantly overcome. So the question is, at any velocity, how much power does the engine need to deliver to overcome drag? Well, in physics, work is the energy transferred by a force over a distance, written as the integral of force dot displacement. Power is the rate at which that work is done, so it's the rate at which energy is transferred. We can express it as the derivative of work with respect to time, or equivalently as force times velocity. In this case, drag is continuously removing energy from the car, so power tells us the rate at which that energy is being taken away at any given speed. That is exactly the rate at which the engine must produce energy to overcome drag. Since power equals force times velocity, and drag force itself grows with velocity squared, the power required grows with the cube of velocity. Let us graph this cubic function. Watch how violently the power requirement rises as speed increases. Now remember that horizontal line representing the engine's maximum power output from our powertrain analysis? Let us bring that back. That flat line is all the power the engine can physically produce. Where our rapidly climbing cubic curve intersects this horizontal power limit, we find a hard mathematical wall. That intersection is the car's absolute top speed. This specific intersection perfectly illustrates the fundamental engineering paradox of Formula One. The racing track is not just a straight line. It is a complex mix of flat-out straights and twisting corners. To be fast in the corners, you need massive downforce, which usually means a larger wing angle and a higher drag coefficient CD. But as you increase that downforce setup, your drag increases, making the cubic power curve much steeper. It intersects your engine's power limit much earlier, drastically lowering your absolute top speed on the straights. Alternatively, if you trim the wings to fly down the straights, lower CD, you lose the aerodynamic grip needed to survive the corners. Setting up a Formula One car is an endless, delicate mathematical compromise between cornering grip and straight-line speed. To solve this downforce and drag paradox, Formula One engineers introduced the drag reduction system, or DRS. Instead of suffering the penalty of a static wing on the straights, DRS allows the driver to mechanically open a flap on the rear wing. Looking at the airflow over the wing's profile, opening that flap instantly changes the aerodynamic geometry of the car. Notice how the massive turbulent wake that normally drags the car backward is suddenly smoothed out and shrinks. Mathematically, this is a real-time manipulation of the terms in the drag equation. It drops the car's frontal area, but more importantly, it drastically reduces the drag coefficient. We keep our high downforce setup for the corners, but we shed a massive amount of aerodynamic resistance the moment we hit a long straight. Let's look at what this physical shape change does to our underlying mathematics. Remember our drag curve from earlier, growing at the cube of our velocity and hitting the hard ceiling of the engine's maximum power output. When DRS is activated and those drag variables plummet, the coefficient of our entire cubic function drops. Watch what happens to the curve. It flattens out. Because the aerodynamic penalty is accumulating at a slower rate, the engine can push the car to a significantly higher velocity before the forces finally balance out. That intersection point between drag and power shifts dramatically to the right. We have essentially hacked the equation, artificially extending the top speed limit of the car without needing to add a single horsepower to the engine. So using the DRS, we can shave fractions of a second off a single lap. But an entire Formula One race is essentially one massive, multivariable optimization problem. Let's map out a simplified three-dimensional mathematical landscape using two of the most critical variables. On our x-axis, we have wing angle. On our y-axis, we plot ride height, dictating the ground effect under the floor. And on the vertical z-axis, we plot the simulated lap time. When we calculate every possible combination, we generate a topological geological surface. High peaks represent terrible, slow setups, but those deep valleys, that is exactly where we want to be. However, engineers aren't just adjusting a couple of variables. To balance downforce and drag, they are simultaneously adjusting variables like suspension stiffness, brake bias, tire pressures, ride height, front and rear wing angles, and more. They must also account for dynamic, real-time variables that change every single lap, like brake temperatures, or like the tire wear, which makes the grip plummet, and that wear is a direct consequence of the compound choice. To find that lowest point, teams use optimization algorithms like gradient descent. Think of it like dropping a marble onto our mathematical landscape and letting gravity do the work. The algorithm looks at the slope of the surface at a given point and takes a step downwards, recalculating the gradients until it settles into a local minimum. This represents the optimal car setup. But here is the catch. This landscape completely changes depending on the circuit. If we are racing in the tight, twisty, bumpy streets of Monaco, the mathematical valley shifts drastically towards aggressive wing angles and slightly higher ride heights. The marble settles in a completely different spot. If we travel to the high-speed straights of Monza, the entire topography warps again, and our algorithm hunts down a new minimum, favoring flattened wings and scraping the floor as close to the asphalt as physically possible. So, next time you watch a Formula One car roll out of the garage, remember, you are looking at a rolling, physical manifestation of millions of solved equations. From the cubic power curves dictating top speed, to the complex friction geometry keeping the tires glued to the tarmac. Every single millimeter of carbon fiber is the result of rigorous mathematical optimization in the pursuit of the mathematically perfect lap.